Start the third day. You guys are doing great, staying with all the presentations. It's a lot of material. Today, we're going to talk about tools. So we're going to start out with the debugger. And it's always been hard when the debuggers say they support GPUs. From the marketing slides, you can never tell what they actually do. Sometimes it's just that they don't crash when you launch something on the GPU, but you can't get any information what's happening on the GPU. And the AMD debugger is excellent. You can get a lot of information all the way down to what's happening on each thread. Let's go ahead and go into the debugger. So I'll show you what information you can get from what's happening on the GPU with the debugger and how to run it. It's if you've used GDB, it's an extension of GDB, so it's not a surprise if you're used to GDB. But GDB can be hard to use if you've never used the GNU debugger. So we'll talk a little bit about what kind of interfaces make it a little easier. So it's based on GDB. It's an extension of it. So it brings in the GDB code and then adds to it. They say it's considered a prototype. It's been very stable, and we've had very few problems with it. Our team uses it quite often for very, very detailed debugging. I'm not sure at an application level you want to use it all that often. You want to avoid using it because there's so much information in there. You're going to spend some time looking through the thousands of threads and data so you want to avoid it by catching the errors beforehand. It works with all the tools that GDB supports, and I'm going to show you some of them that make it a lot easier to use the debugger. There's some exercises that you can follow along and try it out, or try it out on your own code. A warning, you really want a small problem. Otherwise, you're going to be in there a while. This is the problem with parallel debugging, is all of a sudden we have a lot of data to work with to try to figure out what's happening. So it's similar, maybe a little worse on the GPU. So here's a simple Saxby kernel. We've seen this a lot. It's a nice simple example. But we've modified it. So we've reduced the amount of data so that we can find our way around. So we have two groups, each with 120 work items. So how many wavefronts are we going to have? 128 work items, so we've got two wavefronts. Two wavefronts times two groups. So we have four things that we have to follow. So that makes it quite manageable. In a real problem, you may be searching through a lot more information. And we're going to cause this to fail by modifying our source code. And one of the ways we could do it is by forcing it out of bounds at the top lines there. What happens when we go out of bounds on a GPU? You know what happens on a CPU, right? What happens on a GPU? It's similar, undefined, right? It may just run. It may crash, depends on what data it's accessing. Okay, so we always have that guard in our kernels. And at first you may not realize why you have it. And if you leave it out, it runs. So you think maybe I don't need it. You need it. Because when it does crash, it can be bad. So we could comment that out and not do that bounds check. But to make it more reproducible, we're going to comment out the allocation here. And then we're going to synchronize before the exit. Otherwise, some of the threads, the CPU threads or ranks may end before and exit the whole program. So we're going to synchronize so that we don't exit before we can do the debugging. We compile this with HipCC, and we compile it for our architecture. What happens if we compile it for a different architecture? It may not run. Depends on whether the GPU can understand the code that is generated. So it is unreliable to compile with any other hardware than what you're running. You can compile for multiple GFX models. Here we're going to go ahead and do it for GFX 90A, so that's a 200 series. So that's going to be a discrete GPU, and then we're going to run the code. I love this, and boom, here is our expected memory violation. So we see the segmentation fault. Okay. So we're accessing memory. It hasn't been allocated. So it will always give you a memory fault here. It's not maybe, sometimes it won't. It doesn't give you a lot of information here. It just says memory access fault. So we haven't done anything with the debugger yet. So let's see how we use the debugger to find out what's going on. With the debugger, I usually want to find what line it's causing the error, and I can usually figure out why if I know what line it is. So that's our first goal. So here's a cheat sheet of common GDB commands. You'll often see people using very shorthand versions like R for run instead of the whole command. You might want to keep this sheet handy because it's not a fancy graphics interface like some of the other debuggers. And so we're going to run the code under ROCgdb. We just do ROCgdb first. And if we have arguments to the program, we have to do --args to pass it to the program instead of the debugger. So now we get the segmentation fault, and it shows it's in the SAXP kernel. Okay. That's already a helpful information. We know what kernel's failing. Okay, can we get more information? So now we're going to compile with the symbol table for GDB. So we're going to add the GDB option so that we have better information for the debugger. Compile it again. And now when we run it, we get what line number it is, what file, and what kernel. So we have the symbol table. It can give us more information. And what is giving us the seg fault is a GPU, is in the GPU. So we want to find out where in the GPU, what line it is. And here, the first line in red, in the red box, is the CPU line that we're on. And then the second one shows the GPU wave. So we can see from that first line that it's in the HSA runtime. So it's telling us that it's a low-level routine causing a fault in our HSA runtime. So right now the CPU thread is just waiting for everything to finish, and it's going to wait a long time. So on the CPU side, we don't really know exactly what's happening. So on the CPUs, we have 96 cores with virtual threads. We can make that 192 threads. So we have 3 CPUs, total 96 cores. It is best to set this OMP num threads variable to 1 so that we're not having to look through all the threads. So again, we continually have to try to reduce the information that we have to dig through. For MPI, we would put the ROCgdb command just before the program name, and you would debug each individual MPI rank. Okay, so we try to put a breakpoint on line 22, but it reports that it's at line 24. So what is happening here? The problem is there's no line of code at 22. And how do we get the breakpoint to land where we actually want it to be? So we can change the optimization level to 0. If you do 03, it will only let you set breakpoints for blocks of code. So this is pretty common in debuggers. We have to change it to take out all the optimizations so that the line numbers are valid. And now when we do the breakpoint, it's going to be in the right place. Okay. Now, the problem there is you may get different behavior in debug than you do in optimize. So you may end up debugging in optimized and just have to live with the line numbers not being exact, and you can only break at blocks of code. So we do a run command here. We can get a lot of information about the hardware, the threads, and here we can use iThread will give us information about the thread. So we can then show the architecture, and it's showing us that we are on the CPU. Okay, this can get confusing. You may be on the CPU and think you're on the GPU. So this is actually helpful to see where you are. If we put the breakpoint in the kernel itself, when we show the architecture, we're going to see that we're on a GFX 90A GPU. Okay, so we can set breakpoints in the kernel. That's the first step you want to do. Get in the kernel. Now let's see what we can see. It helps to have these graphical user interfaces. So there's a variety of them for GDB, and one of these will probably be on your system, not all of them. So we can do ROCgdb-TUI. TUI is a text user interface. So it draws a box, but it's using text characters. And that's actually a plus, because when you use a graphical user interface and you're doing it remotely, it can be very slow. So it's actually an advantage that we have a TUI instead of a true GUI. Okay, I'm going to date myself here. I don't know how many of you are going to recognize this. What is CGDB? So that is curses GDB. How many of you know what curses is? Oh, you're dating yourself too. So curses is an ancient database which would map the commands that the computer would send to the terminal type you had, like term, what is it, 102 and VT 102. I've forgotten them. It's been so long ago, but it would actually map how to draw things on your screen in the primitive text user dates. So if you understand CGDB, you're dating yourself. But it's kind of neat because it also gives you a graphical or a text-based window. And in both of these, you see the lines of code at the top and your command console at the bottom. This gives you an idea where you are in the program, and it makes it a lot easier to navigate. Okay, so I strongly recommend using these with ROCgdb. And each of them shows, it's hard to see on this small screen, but when you set a breakpoint, it's going to show it right along the lines of code, so you know where your breakpoints are. Here's a really slick one if you really want to go deep. This is GDB dashboard. It shows all the registers. It shows the stack, the variables, the assembly code. You need a big screen to see all of it, but it's pretty awesome, the amount of information it's giving you in this text-based user interface. So if you're going to do debugging, this might be very, very useful. And it's a open source project. We also have more of a GUI interface here that we can use with this GDB GUI. That's going to be slower to work with, but it's not too bad. And then let's go back over our architecture. So we have a SIMD unit here. The L1 cache is here, the scalar unit and the scheduler. So we're going to look at 4 waves. So we're going to see 4 SIMD units being used. And from ROCgdb labels these a little differently. So it's going to treat a SIMD unit as a core, executing up to 10 threads with a vector length of 64 lanes. So it's a little bit different view of it than what we typically label the hardware. We can list, so we can get information about the threads on the GPU. And you're going to start to see, for example, you can see the different work groups here. There's 2 work groups and 2 waves for each work group. So that each of those numbers gives you information about that. Here's the decoder ring. So we can get the QID, the wave ID over here. So we got 1 through 4. We can get what work group we're on and up to 3D. We're only doing 1D here. So and then we can get the wave ID. So we've got a lot of information, but if you're really debugging something deep here, it's going to take an effort to track all that information, especially if you have 1,000 data items that are running on the GPU. That's why we want to get it small. So you can modify the registers just like on the CPU. You can modify memory or LDS. It's pretty amazing. that you can do all this on a GPU. The debugging was much, much harder early on the GPUs. And you can step through the one instruction at a time. And even look for race conditions by how you step through the code. Now, if you have a race condition, it's going to behave differently in the GPU because you're running slower and you're maybe only advancing one thread at a time. Okay. We can also get more information about the devices and properties. So we can find out what series of GPU we're on. We can find out how many SIMDs we have, which is 4 times the number of compute units, and the max waves. So we can get a lot of information here that the debugger will show us. We can get information about the queues. So if we're doing streams or hardware queues, we can get information about that as well. We can get information about kernel dispatches. So we can see what kernel is being launched on each of these. Now, that's a lot of information. So before you start diving into the debugger, try to use your other tools first. And one of them is AMD log level. And we set that to 3 as we're running. And you will see a lot of information here. And quite often I will do this to see what the last line is that I see. That'll give me some hint where it's crashing rather than firing up the debugger. So even though the debugger is awesome, I really recommend trying to avoid using it. It's really a tool of last resort, just because of the amount of time it takes to do things. Here's another GUI interface with Chrome. You can use X forwarding for the GDB window to remotely. There is some pretty good documentation here, and basically the ROCgdb is like the whole GDB manual plus some additional pages for the GPU. The reference card is kind of valuable if you want to keep something handy about what all the commands are that you can do in the debugger. I do like some of this. These are older, especially Andrew's presentation, but I think it's a good way to see what you can do with the debugger. So it is a 24-minute video of debugging GCC code. That's with OpenACC and OpenMP. So GCC supports both of those. And that might be interesting just to see what you can do. And Justin Chang, who's on our team, has a presentation as well. That's everything on the debugger. I'll pause for comments or questions on it. Debuggers are kind of dry, but they're really important when you need them.
It's been a while since I've parallel debug. I think I used something like called Total View or something.
So Total View, and it's got a nice GUI interface. Yeah. My daughter calls it kindergarten button.
Yeah. Yeah, it was heavy, I remember, but useful. But how, in this case, I can't remember anymore. But so if you step through the code and there's an offload to the GPU, then it steps onto the GPU essentially. What the GPU's
going to start on the CPU, yeah, and then go
jump
down
over
the
GPU, right? And then every instruction is like synchronized in time, right?
Yes.
Or so you can, okay,
If you do, so there's two commands. There's next and step,
yeah,
and one of them,
goes into the,
they all move forward, and the
Yeah.
other one only moves one of the threads forward.
okay.
And,
Ah.
and I have to remember what it is. That's why you need the cheat sheet.
Okay,
And, yes, the GUI is really nice, but it's heavy. The commands are much the same. So, next runs the next line of the program. Oh, no, step dives down.
That's right,
So
yeah.
next will stay in the file you're in, but
yeah, that's right, and then,
Yeah.
okay, yeah, so, but what happens? So there's no, is there a way to see what the CPU is doing while the GPUs are running? Like,
yeah,
How
they
do you
were
do that?
showing you that you could switch between the GPU and the CPU.
okay, but as you step through code, you go next, or step into the
Yeah, you're
GPU,
gonna
then
be now
what
down
happens?
in the GPU.
Yeah. No.
So you gotta do an up
Ah.
command to get out of the GPU.
Okay, but in reality, the CPU should be continuing, right, in your product.
Well, we
Run.
put a synchronize in there, so it should
Okay.
block and wait.
It should be, okay, I see. And if
That's
you want
why
the
we
CPU to
put that
continue,
synchronize in.
right, if you want the CPU to continue, you have to go back up and then.
Do an up and then
Okay.
step or next.
Nice.
Yeah. Yeah, so you're gonna, as soon as you, say, I gotta use the debugger, you better plan, clear your desk, clear your schedule. You're gonna be in it for 2 or 3 hours, and you're gonna be very deep in it so that you have to really concentrate. But it is pretty awesome that you can see all this today. Now, TotalView and DDT say they support the AMD debuggers. I do not know the level of their support, whether they show this level of information or not. The Cray debugger is basically the ROCgdb with a little bit of extra that Cray puts on top. Yeah, I would hope that TotalView and DDT would give you at least some of this information today. I just don't, I haven't tried.
But this seems plenty useful, so.
I think this is more useful
Yeah.
just because we're seldom on the computer, so we want something that will respond faster. If you're gonna use TotalView and DDT, you're really gonna wanna have a remote desktop set up where, and we'll talk a little bit about that in the system administration. But I want something which is responsive so that when I press that little kindergarten button, it does something. Yeah. Okay. Any other questions on the debugger? How many of you have used GDB? Hey, that's impressive. I hadn't used GDB a lot before I started using ROCgdb. I have used TotalView a lot.
So I much prefer GDB because it's so fast, but it just, for the parallel, I didn't know how to use GDB properly, or I think on the system I used it, it wasn't really supported. GDB parallel debugging.
Yeah,
No choice
so
but to
in
use
parallel,
TotalView.
you're gonna have two windows open, right?
Yeah.
And if you got going beyond 2 to 4th ranks is crazy. You might just debug one and let the others run. There's ways of doing that, saying if I'm on a certain rank, run the debugger.
One of the problems with like debugging real code, I found always, like you said, is that in debug mode, it doesn't crash. No one optimizes, crashes. But the other thing is, I find it's also problem size dependent sometimes. So if I reduce my problem, like reduce the number of grid points in a fluid dynamic simulation, then suddenly I have much more diffusion, right? And then it doesn't crash anymore.
Right.
So I was wondering if you could somehow debug a code at the high resolution, but only somehow isolate or try to first figure out where in the grid something happens, But I don't know,
So my recommendation there, and I've worked on a lot of different code projects where they didn't do this, so this is why my recommendation. You really want to have a lot of unit tests
yeah,
at small scale so that you get those bugs out at that scale and where you can reason about them. And if you have to, you go through it with debugger. And so many code projects, and I've been on these where you're running 1,000 processors 5 days into a run and it's crashing. That's hell. And then you find out it's not exactly the same iteration it crashes on. So the other thing you want to do is use tools. So and I got a whole chapter in my book on tools. Use the memory tools to look for uninitialized memory. Though that's an insidious bug, really hard to track down. And so if you run your unit test through with the uninitialized memory, it will make your code far more robust. And do that at small scale. I had one problem where it was all of a sudden the memory usage on the node was jumping like 20–30% 5 days into a run on 1,000 processors. And it wasn't repeatable, so we'd run it and try to figure it out. Was it a particular version of MPI? Was it a particular version of the PGI compiler we were using? We could never track it down. It's really, really hard when it's that far into a run. Most sites will do what they call a DAT, a dedicated access time, application or access time, where they will schedule you for 8 hours so you can debug that scale, but really don't want to. Cray does have some really nice tools to debug at scale. The open source ones aren't quite as good at 1,000 processors, but we don't want to be there, right? We don't want to be at 1,000 processors. Now we got MPI ranks, OpenMP CPU threads, and GPUs. So it just gets progressively more complex. You do notice that you can print out variables. You can actually print out variables from a kernel. Some output, not a lot of output. So you can just put a print statement in. But you can also print from the debugger. And I think all of us fall back on this where we start printing out things in parallel jobs because it's just really hard to keep in your head what this rank is doing versus that rank. And is this one running ahead? And is that what's causing the problem? So parallel debugging is a real art form. Okay, so I think we're at the end of the presentation time. There are some exercises you might try and at least fire up. I don't know which one of these is working on AAC6, so it might be good to find out. Let's see. For GUIs, it's usually either ROCgdb with -2e or CGDB. One of those two is usually present. I don't think I installed that other tool that you have to download that self and download that yourself and try it out. But it is pretty awesome. Somebody recommended that to us at a training. just being able to see the assembler is pretty amazing. Not that you need to read the assembler, but it can give you clues on what the compiler is trying to do. Yeah, and if in the early days when the debuggers weren't as good, what we would do is we would send in an extra array into the kernel, then write into that array, bring it back to the CPU, do a mem copy back, and then print it out. And that was actually pretty effective, but it was time consuming. You may still want to do that if you're really getting lost what's happening.